In this video, we're going to talk about Newton's method, which is another application of this idea of linearization. The idea that if a function is differentiable, then it can be approximated using its tangent line close to the point of tangency. So we're going to use this linearization to find the zero of a function. And our calculators, I don't know if our calculator uses the exact Newton's method or something very close to it. But when you find the zero using your calculator, it's doing, if not Newton's method, something like it. So the idea is we're going to start with a guess. So first of all, we should say this is what we're after. So when polynomial or some function crosses the x-axis, we would like to know where does it cross the x-axis. Where is that zero? So what we do is we just make a guess first. So we'll call that, say, x sub 1. And we'll take that value of x and run it up to the curve. And then we'll find the tangent line to the curve at that point. We'll extend now, remember, a tangent line acts a lot like the function as long as you don't go too far away. So we're going to now find the zero of the tangent line. That is, we're going to imagine we extend that down to where it intersects the x-axis, and we'll call that x sub 2. That's going to be our first guess. Then we'll repeat the process. So we'll take that next, oops, I got the wrong one there. Let me try that again. I got to fix my axis and fix my tangent line. Okay, so then we'll take this approximation, run it up to the tangent line, and then we'll find a new tangent line. And then we'll run that tangent line until it intersects the x-axis, and that will be our next approximation. And we keep doing this until we get as much accuracy as we desire. So let's see what that looks like. So when we have this tangent line at x1, then remember, because this value of x1 is on the curve f of x, that means its y-coordinate is going to be f of x sub 1. And we know the slope of the tangent line is going to be the derivative evaluated at that x sub 1. So that makes the tangent line, that red tangent line, y minus the y value is the slope times x minus the x value. Then when we go to solve that, when we want to find where this is going to cross the x-axis, we plug in 0 for the y. And so we get 0, and then if we're going to, we put 0 in for the y, which makes that a negative f of x sub 1 is equal to f prime of x sub 1 times x minus x sub 1. This is what we're trying to solve for, is this x2. What value of x will make this tangent line equal to 0? So we'll divide the derivative over. So that's now going to be negative f of x sub 1 over f prime of x sub 1 is equal to x sub 2 minus x sub 1. We'll add the x sub 1 over, and we'll get, I'm going to come this way with it, x2 is equal to x sub 1 minus f of x sub 1 over f prime of x sub 1. And so that x2 that we're finding here is that next approximation. And then we can repeat the process again. And what we get is what's sometimes called a recursion formula. We say this is iterative. We repeat it over and over again. So we can say x sub n plus 1, the next guess, is going, or next approximation is going to be the previous approximation, x sub n, minus the function evaluated at that previous approximation divided by the derivative evaluated at that previous approximation. This is Newton's method. And it works really nice and quick and efficiently on your calculator. So let's see how that might work. So we're going to look at f of x equals x cubed plus 3x plus 1. So graph that. You can just go zoom 6 for a standard window. And when you look at that, I think you'll see it looks like that it crosses the x-axis somewhere between 0 and -1. So it's going to look something like, if there's -1, it's going to do something like that. So this is what we're trying to find. So let's just, so that we do this the same, let's just choose our first guess to be a -0.3. So sometimes this first guess will be given to you. Other times you're going to have to do something like what we just did there. So you just have to communicate what you're using for your first guess and then go from there. Now we need to know what the derivative is. So this we have to do on our own. F prime is going to be 3x squared plus 3. So then what we're going to do is following that formula that's in the box in white there, we're going to say our next guess, x2, our next approximation, is going to be our previous one, which is going to be the -0.3 minus the function evaluated at -0.3 over the derivative evaluated at -0.3. So to do this really efficiently, what we can do is we can put in as y1 our function, and if we in our calculator, and if we plug in y2 as the derivative, we plug the derivative in as y2, then what we can do is if we go -0.3 and then hit enter on our calculator, I'm sorry, -0.3, and then you can store, you can hit that store button, which is right above the on button there, and then you'll see a little arrow show up, and then hit the x comma t comma theta button, and then hit enter, and that will store our -0.3 as x. Then in the next line, we can do essentially what you see right in here. So we can go x, which is our -0.3, minus, and then y1 of x divided by y2 of x, and then hit that store button again, and hit x again, and then hit the enter. So what that's going to do is it will kind of set a formula right in here in your calculator. And so when you hit enter, you should see on your screen something like -0.32232, on and on and on. Now, if you just hit enter again, the calculator is going to repeat this thing that it just did on the screen, but because you stored this as a new x, the value it's using here now is our -0.32232. Now you'll need to write down x2 is equal to this. So this is going to be our x2. And then when you hit enter, it's going to repeat that process, and it's going to give us our value for x3, just that quick and easy. And that, I think, is going to be like a -0.322185, and on and on and on. So you can see how much accuracy we are creating here by the agreement we have in these successive terms. So the decimal places that have agreement are now correct. So we can see that we already know what that 0 is to 3 decimal places. It's going to be a -0.322. And when you do that another time, this is now we're up to x sub 4. So that's going to be then a -0.3221853, on and on and on. So now we have agreement with the 322185 and so on. So we can already see that we have our answer correct to 6 decimal places. So it won't take very long before you'll get agreement to as many decimal places as our calculator can show, and so it goes usually really fast. So Newton's method usually converges very quickly, and if it does converge, that if it does go get closer and closer to a single number, then that number is in fact a zero. Now let's go to a new panel and we'll see what things might go wrong. So some of the things that can go wrong. Now remember, our Newton's method is x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So one thing that could go wrong is if you make a guess and then on the way to trying to solve this Newton's method, to find this zero, along the way the derivative ends up being zero. And so what you end up trying to do is divide by zero, which doesn't work. So we could end up along the way with f prime at one of those intermediate steps is equal to zero. But that's not generally a major problem. You just pick a different first guess. So pick a different x sub 1, your first guess, and then that should hopefully dodge that issue and you'll be fine after that. Now, what's trickier that there isn't really a good resolution to is you could do something like, I'm going to try to demonstrate it here if I can. So you make your first guess here, and that takes you up to right here. And then you find your tangent line to the curve there. And let's see if I can kind of make that. So suppose that hits there, and we go down, and then this then becomes our first approximation. And so we repeat the process. We come down to here and we go to find the tangent line, and lo and behold, that tangent line takes us right back to where we started. And so now we've got a major problem because it's just going to keep bouncing back and forth between the two, and you get caught in an endless loop. And that's not there's no good solution that I'm aware of for that. We're going to see one, do an example with you later where it even goes a step further, where you make your first guess and then the next iteration takes you further away from the zero, and then it goes even further away. So it might look something like, the next guess is going to go further away, and then that takes you up here, and you go further away still. And so it's not closing in on anything, and so it's not going to find the zero there. Now, one other thing to be aware of, you have to be a little careful sometimes, and you see that on a calculator when you're finding the zero and it asks you for a guess. Some functions, particularly if you're trying to find a zero that's pretty close to a vertical asymptote, you have to be really careful about what your first guess is. Now, if Newton's method does converge, it will converge to a zero, but you may not get the one that you're trying for. So in this example here, we're going to try to find this zero right here. But we'll make our first guess and say we go right here is going to be our x1. So we come up to the curve right here. We find our tangent line, and we extend that over to where it crosses the x-axis, and that's going to be right here. And so then we, this is now our x2. We try to repeat the process, but now we get our tangent line, and it's going to go over here. And now all of a sudden, we're going to start homing in on a zero, but the zero that we're going to find isn't the one that we wanted. We're going to end up with that zero over there. And so sometimes what happens is you have to be very careful where you make your first guess. Okay, let's see an example where Newton's method fails. So I'm going to slide this up a little bit. So let's say that, an example where Newton's method fails. So we're going to say f of x equals the cube root of x, which we know can be written as x to the 1/3. So you can sort of see, if you imagine what the graph looks like, you might have an idea of what's going to happen here. So if we make our first guess, say, let's make our first guess, say 0.1, then we know our f prime of x is going to be 1/3 x to the negative 2/3. And so we can enter again like we've done. We'll put f of x in as y1. So we'll call this our y1, and we'll call this our y2. And we'll practice that. We'll go 0.1, and we're going to store that into x and then hit enter. And then we will do our x minus y1 of x over y2 of x, and we'll store that result as a new x and hit enter. And so the first time you hit enter, now we know where the 0 is on this cube root function. It's going to be at 0. So we were guessing 0.1, so we're pretty close. We're only 0.1, excuse me, we're only 0.1 away. But what we're going to get for x2 is going to be a negative 0.2. And so now we already have a sense that something's not going well here, because negative 0.2 is further away from the 0 than was our original guess, 0.1. If you hit enter again, then your next guess is going to be a 0.4. And so you can see what we're doing is we're careening further and further away, and so this is not going to converge to anything. It's not going to get closer and closer to anything, and we're just not going to be able to use Newton's method for this particular example. So let's do one where it does work. So let's use Newton's method. So we're going to use Newton's method to approximate the square root of 2. So we need to first come up with a function that has square root of 2 as a 0. So if you think about that a little bit, we could say maybe f of x is equal to x squared minus 2, right? Because if we were going to solve that, we would get that positive and negative square root of 2 would make that be 0. So this is going to be our function f. And we know its derivative, f prime, is going to be 2x. And let's choose for our first guess, let's call it x sub 1 is 1, just so we can agree. And then see if we can do this. So I'm getting, for my second guess, is 1.5 from, I guess, would be my first approximation, because I guessed 1, we guessed 1, and then we did our that whole routine that we did over here, and we got I got 1.5 for the next one. When I hit enter again, we're getting x3 is 1.41, and then it's repeating 6s there. So let's see if we can find this to 5 decimal places of accuracy. So we're going to go to 5 places. So I'm going to hit enter again, and now we're up to x sub 4, and this is going to be 1.4142156686. So let's see, we've got agreement to the 10th place, the 100th place, and that's it so far. So we're going to go to x sub 5. I'm going to hit enter again. So hitting enter again, and now what I'm seeing here is a 1.4142135562. So we have agreement now we have the 10th place, 100th place, thousandths, 10 thousandths, 100 thousandths, and then we don't have agreement after that. So far we have 1, 2, 3, 4, 5. Now we do know that whatever that place we don't have yet is going to be in between the 5 and the 1. So we have enough that we can approximate it to 5 decimal places because we know how to round that. Well, let's go one more just to be sure. So now we can see that we have 3 in that next place. And so we can say to 5 decimal places, it's going to be 1.4142, 1, 2, 3, 4, 1. And then I know that it's going to round down because the next one's actually going to be 3. So there is our 0 to 5 decimal places. Very good.